Okay, so I'm just going to be working through problems 3.2, 3.3, and 3.4 from the Minifloat lecture. And in all three problems, we're giving a binary representation of a Minifloat, and we want to convert it back to decimal. So the first thing we can do is just break down the value we're given into its three parts. We know we can separate it into 1 bit for the power, then 3 for the biased exponent, and then 4 for the significand. And then we can go ahead and start converting it back to decimal. So you might be tempted to go ahead and figure out what the value of this exponent is. That's a 1 plus 2 plus 4, which is 7. And then you might want to say subtract 3 for the bias. So we have a 2 to the 4th as our exponent. But that's actually wrong in this problem. And that's because there are some special cases for floating, for Minifloat, and those are just by design. And the first case to be aware of is when you have all ones in the exponent field, and that's going to imply that you're looking at infinity. So then the next question is, we have all ones, we know we're looking at infinity. How do we differentiate between positive infinity and negative infinity? And the answer is we look to the sign bit. That still applies. So if it's 0, we're looking at positive infinity. Otherwise, if it was a 1, we would have been looking at negative infinity. So in this case, we know we are dealing with positive infinity because that first bit's a 0, and we are having a special case where the exponents are all 1s. And these two slides from lecture are relevant. There's 4 different exception cases we want to look at. We have the 2 infinities, not a number on this slide. And then the last one, you don't want to forget about denormalized values. And that's when you have all zeros in the exponent field, and the workaround is that you just have a implicit leading 0 in your significand. So let's look at 3.3. Let's go ahead and do the same thing where we break it into its 3 parts. We have a 0 for the sign bit, 0s for the exponent field, and then 0, 0, 0, 1 for the significand. And you might, once again, be tempted to go ahead and calculate what the value of this exponent is, except as we just went over, there's a special case when all the exponent field is zeros, and that's we have a denormalized value. So what we want to do here is, for the exponent, you essentially take the lowest value that isn't denormalized, and so the lowest value that isn't denormalized is if we had a 0, 0, 1, and then we still have to subtract our bias, so 1 minus 3 is going to equal negative 2 for the exponent. So we have 2 to the negative 2 times, and then normally in Minifloat we use a implicit 1 point, and then there are 4 values. For the denormalized case, we'll actually use a 0, and that's what's different about this problem. So we'll do 0.0001, and then this right here is 0, meaning that we're looking at a positive value. So let me go ahead and add in an extra 0 here, and then we can, we know we have to left shift twice because we're looking at power, we're base 2. This would be the same as scientific notation in base 10. If you have like 56 times 10 to the second power, you could just move the decimal place over 2 times to the right. We'll do the same thing since we're in base 2, except since we're negative, we'll go left 2 spots. And so then our binary representation of this number is 0.000001. And the last thing we need to do is convert this back to decimal. And so we know that this is 2 to the 0 power. So this is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4, 2 to the negative 5, and 2 to the negative 6. So 2 to the 6 is 64. So we have 1 over 64 is our value in decimal, except we need to give that with a decimal point notation, not a fractional form. So we're going to defer to long division. So we have 64, and then I'll just add some zeros. Doesn't go in the 1, doesn't go into 10. It'll go into 100 once. And so we can do that subtraction for 36, we'll drop the 0. I'm just going to do this a little bit fast because my knowledge of long division is pretty bad. 64 goes into 360 roughly 5 times, because 5 times 60 is 300. So then that'll be 300 plus 5 times 4, which is 20. So then we'll have a 40, and we'll go ahead and drop the next 0. And then we can say that 6 times 60 is roughly 360. So that's how we can use that one. And then 360 plus 24 is 384. And that gives us a 16 down here. And then we have a 160. And we know that's 2 because 2 times 60 is 120. So that's 128. Let me add an extra 0 or 2 here. And then 160 minus 128, that's going to be 30 or 42. No, that's going to be 5, 10 to 32. And then we'll drop another 0. And we know that that is actually 60 times 5 is 300. And 5 times 4 is 20, so that's 320. And we get the 0, and we stop right there. So then that gives us, this is our final answer, 0.015625. Wow, that was a lot. Okay, so then let's move on to the last one. And we'll do the same thing. Let's go ahead and break it into its 3 parts. We have a 0 for the sign, 1, 1, 0 for the exponent, and then all 1s for the significand. So this is not a denormalized case or any of the exception cases, so we can treat this one totally normally. So let's go ahead and compute the value of the exponent. We have a 0 plus 2 plus 4, so this is 6 in base 10. And then we have a bias of 3 in base 10. So our value of exponent is just 3. So we have 2 to the 3 times 1 point this 1, 1, 1, 1. And we know it's positive because this is a 0 right here. So we can go ahead and move the exponent over 3 times, 1, 2, 3. And then our final answer is 1, 1, 1, 1.1. That is in binary though. And if this part wasn't clear, I can give a better explanation if someone just asks. I don't know if you've covered that in class though. So the last point is just to go ahead and convert this to decimal. So we know that this is a 1, 2, a 4, and an 8, and we know that's a 1/2. So that's going to be 12 plus 2, 14 plus 1 is 15. So we have 15 and then 1/2, which is just the same thing as 15.5. So that's going to be your final answer. And then I guess just for notation, that plus sign is going to be there. So yeah, that's how you do questions 3.2 through 3.4.